This is the first lecture in a series of pre-calculus lectures sponsored by Math-Based Tutoring. If you need any kind of tutoring, please feel free to visit us at facebook.com/mathbasedtutoring for a reasonable price and online tutoring for not just pre-calculus but any other kind of mathematical tutoring that you may need, all the way from 3rd grade to upper level college material. We cover a lot of different topics. But this lecture today is going to cover the subsets of the real numbers. And real numbers are numbers that we use a lot in calculus. And I'm going to talk a lot about calculus because this class is designed to prepare people for calculus. So we're going to talk about the real number system and their subsets. And real numbers are denoted by this big script letter R. Okay. So the first subset of real numbers that we are going to discuss are the natural numbers. And these numbers should be numbers that come natural to you. And I'll give you an example. If you were walking down the road and you saw a pile of money on the road, like a pile of $1 bills on the road or $5 bills, the first thing you would do is pick them up and count them naturally, right? It's natural to count objects that we see, that we don't know how many we have. And that is what the natural numbers are. Just the numbers that we count with. 1, 2, 3, 4. And this little dot, 3 dots, is called an ellipsis. It means that this set of numbers, set being just a group of numbers, this specific set of numbers continues indefinitely forever. They go on and on and on infinitely. And we denote the group of natural numbers by the capital letter N. So if I say something belongs to set N, I'm talking about the natural numbers. Okay. Now, there's one property about these subsets of real numbers that I want to discuss that becomes important later in mathematics, and that is closure. Closure. What is closure? If I say something is closed, it means if I take two numbers in a set, so I take two numbers from a set, say 2 and 3, and perform a mathematical operation on them. So I take these two numbers and say add them, and the result is also in the set. We say that that operation is closed in the natural numbers. For example, addition is closed in the natural numbers. Okay, that's an important property of the natural numbers. What that means is if I take any two numbers in the natural numbers and add them up, the result will be in the, so if I take A plus B, the result C will be a member of the natural numbers. Okay. The natural numbers are closed under addition. Okay. The natural numbers are also closed under multiplication. If I take two numbers and multiply them, A times B, and multiply them and get some number C, that result is going to be a natural number also. Okay, that's what that means. So the natural numbers are closed under multiplication. Now what about subtraction? If I take two natural numbers and subtract them, will my result be a natural number? What if I take 3 minus 4? That would be -1. Is -1 a natural number? No. So the natural numbers are not closed under subtraction. What about division? If I take 1 divided by 3, is that result going to be a natural number? No. Because 1 divided by 3 is 1/3. So we say the natural numbers are not closed under subtraction and not closed under division. Okay. So the next set that we're going to look at are the whole numbers. And the whole numbers have the same closure property as the natural numbers. The only difference between these two sets is that we have the number 0 introduced. So they have almost the exact same properties. The only difference is 0. Okay? And those numbers are denoted by the letter W. Okay? So basically for a long time, those were all the numbers mathematicians worked with. And that's obviously not enough numbers to satisfy all of the calculations in the world. So we needed more numbers. And the next set of numbers that came about are the integers. The integers. And the integers are the whole numbers and their opposites. So we introduce negative numbers. Okay? Negative numbers. So these start at, say, negative infinity, and they go from -3, -2, -1, 0, 1, 2, 3, and so on. Okay? When we call these, we use the label we use for these are the script letter Z. Okay? Z has something to do with the German language and the word integer. That's where the letter Z comes from. So if I say something belongs to Z, that means it's an integer. Okay? So, what about the closure properties for integers? Obviously, all of the whole numbers and all of the natural numbers are in there. So the integers are closed under addition. Under addition. And they're closed under multiplication. What else can they be closed under? Well, the integers introduces another operation, and well, let's look at the two examples that we had here earlier. 3 minus 4 is -1. Well, -1 is an integer, so this satisfies one of the we could say, what about -3 minus 4? Let's change some signs up. Would that be an integer? The answer is yes. That would be -7. So, well, this property obviously isn't going to work because 1/3 isn't an integer. So we say that the integers are closed under subtraction. Okay? The integers are closed under subtraction because the result of subtracting two integers is going to be an integer. So now we needed another kind of number, because obviously these numbers are not enough to satisfy all of the situations that we could possibly have. We need to be able to divide numbers and have a result. Thus, the next set of numbers that we're going to discuss, the next subset, are the rational numbers. And the rational numbers are denoted by the letter Q. Rational numbers. If we look at the word rational, let me write it here. The word comes about from the prefix ratio in here. Okay, and a ratio is a fraction, okay, a quotient of two numbers. That is a ratio. Okay, so the rational numbers are a quotient or a ratio of two numbers, A and B, where A and B are integers, and very important, B cannot be 0. You cannot divide by 0. So that is the exception in the rational numbers, is division by 0. Okay. Let's discuss why we can't divide by 0. Let's say that I say the number x, okay, the variable x, is some number m divided by 0. Okay, so I want to solve, say I want to solve for m. Okay, I should be able to multiply both sides of this equation by 0. If I do that, then I get 0 times x is equal to m. Well, this is not possible because I said that m is any number. And we know that 0 times any number has to be 0, so this is a contradiction. Therefore, division by 0 is not possible. Division by 0 is not possible. Thus, we just say division by 0 is undefined. And if we include this case that division by 0 is not possible, then we can say that the rational numbers are closed by addition, subtraction, multiplication, and division. So if I divide two numbers that are rational numbers, the result will be a rational number, with the exception that we include that the division by 0 is not possible. Alright, one other big property of real numbers. Real numbers. What makes something real? You can see it. So, when we look at properties of numbers, and I'm just going to talk about the rational numbers, we want to graph them, because I haven't discussed all the real numbers, but let's just talk about rational numbers. Rational numbers can be visually graphed on a number line. There isn't a real number that you cannot visually graph to compare them with. Okay? Rational numbers can be visually graphed on a number line. And people like to see, people like pictures and represent things with pictures and graphs and graphing so that you can see how a function works. Okay? So what do we need to graph a number line? First thing we need is a horizontal line, and we put an arrow on one side of the line, particularly the right side of the line. What this means is that the numbers will be increasing from right to left. That's why this side doesn't have an arrow on it. And when you get into the Cartesian plane, you'll see two lines. But for now, we're just going to have one number line, increasing from left to right. Okay. Now the first thing we need to have on here are the two major important points. And the first one indicates where 0 is. Okay, that's a coordinate that indicates where 0 is. If most of your numbers are going to be positive, you want to put your 0 on this side of the graph so that all the numbers can be over here. Or, if most of your numbers are negative, you'll want 0 to be over here. Okay. Now the second coordinate that you put is very important. It can be on the left side or the right side. I'm just going to put on the left side. Okay, this indicates the scale, and we write the word scale, of the graph. So if I chose this first number to be 2, that means that each corresponding coordinate, which has to be is equally apart, is going to be 2 apart. So as you can see, there's not a whole lot of room for me to get too far. That means that this graph is really only going to be able to cover the numbers of 1 through maybe 12. I probably have room for 12 on here. Okay. So this first point is important. So if you want to graph the number 5 million, you wouldn't be able to use a scale like this. Okay. If you wanted to graph 5 million, well, first of all, you'd want your 0 to be over here. And we could just say that the first number is 1 million. And I'm just going to write an M for 1 million. And the next coordinate would be 2 million, 3 million, 4 million, and so on. And if I wanted to write the coordinate for 5 million, we could put it right here. Okay, 5 million. So this first scale, and I know that I'm just drawing this with a freehand, so in most of your graphs, I don't expect you to get a ruler out and draw the, that's what you should do, but most people aren't going to do that. So try to be really, kind of accurate about how far apart these scales are. Okay, so all of the numbers between 4 and 5 million are recommended. If there's a lot of places that I need to graph between these two, if I needed to put maybe 4.1 million here and 4.7 million, there's not a whole lot of places that you can graph between here. So be careful also, to leave enough room if you're going to graph a lot of different numbers between each little thing. But the idea is that you just have a good idea how big that number is compared to 12, right? This is a whole lot bigger than 12. Even 12 should probably be even closer to 0, right? So graphing numbers just gives you a visual scale of how big these numbers are. So, have we discussed every type of real number? We can put rational numbers on these lines too. Let's say we want to graph some fractions. You just need to be careful and make sure you draw a straight line, not a crooked line like I just did. So I'm going to put my 0 here, and maybe a 1 here, and a 2 here. And I want to graph 3/4. Well, I know that's going to be about 3/4 of the way between 0 and 1. We just put it right there. 3/4 lives right there. And maybe 7 thirds, which is 2 1/3, 7 thirds could be right here. These are just coordinates that identify the location of those two. So 7 thirds is bigger than 1/4. You can see that from the picture. Now, obviously, we haven't covered all the types of numbers that there are. Are there more types of numbers? But before I do that, I need to talk about one more property of rational numbers, other than closure. And that's their decimal. Okay, the decimal form of rational numbers. And then maybe you can think about more different kinds of numbers. Those of you that have had a little algebra already know the answer, but those of you who have not, let's look at 1/2. We know that 1/2, if I take 1/2 and put it into decimal form, that means I'm going to take 1 divided by 2. And 1 divided by 2 is written like this. Okay? That's 1 divided by 2. So 2 goes into 10 5 times, and the decimal stays, and 2 times 5 is 10. And so, what do you notice about this number? It terminates. So the decimal terminates. That's one property of rational numbers, is that their decimal can terminate. Well, let's look at 1/3. Pretty close, but very different. So that'd be 1 divided by 3. And we're going to need some zeros here. And this is what I like to call keeping an idiot busy. But we will not go for eternity. 3 goes into 10 3 times, and 3 times 3 is 9. And when we subtract, we get 10 again. And 3 goes into 10 3 times. 3 times 3 is 9. We get 10 again. Notice that the 3's repeat forever. Okay. rational numbers either terminate or infinitely repeat the same set of numbers. In this case, 3. But actually, all rational numbers actually infinitely repeat the same set of numbers. In this case, what repeats? 0 repeats forever. Okay, we just don't write it that way. Okay, we just say it terminates if it ends with 0. But technically, we could write zeros up here forever too, and we wouldn't be incorrect. Now, instead of writing ... the most common way of writing that a number repeats is to use what is called a repetend, and we say 0.3 bar is equal to 1/3. Okay, this symbol here is called a repetend. Okay, so now that we know that we have patterns of numbers that infinitely repeat the same set of numbers or terminates at a certain decimal, these are rational numbers, quotients of 2 integers. Are there any other sets of numbers? Well, what is the opposite of terminate or infinitely repeat the same set of numbers? Never terminates would be the opposite. Never repeats the same pattern of numbers. And what kind of numbers are those? Well, they were found when we were talking about when right triangles were being explored, and where they were using the Pythagorean theorem. I remember a squared plus b squared equals c squared. So if this is a, and this is b, and this is c, they say that a squared plus b squared equals c squared. Now, there is a triangle that exists such that both of the legs are 1. Okay, the legs are a squared, a and b. So let's plug that in. We'd get 1 squared plus 1 squared is equal to c squared. So let's simplify this out and solve for c. 1 squared is 1 and 1 squared is 1. So this result would be 2 is equal to c squared. So they're looking for some number that multiplies itself together to be 2. And we're about to prove this. This number cannot be expressed as a quotient of 2 integers. And the decimal form never terminates and never repeats. Therefore, it is not rational. It is irrational. It is irrational, not rational. And irrational numbers are I. Okay, in most cases they use the letter I. Irrational numbers. So let's use the calculator to see if we can find the decimal form of the square root of 2. Okay, the decimal form of the square root of 2. And this is the TI Inspire. So let's take a look at it here. The square root of 2. And what helps us with the TI Inspire here is that it has powerful fractions. So if I approximate the square root of 2, Control Enter. And I want more decimals than that. And I'm not sure how to do that. Let me see here real quick. Well, these are enough. Okay, of course if I hit answer square I'm going to get 2. Okay, but realistically that is not enough digits to even come close to the square root of 2. And let me explain why. If I write this as a fraction, this would be 1, let's just look at 141 over 100. Okay? 141 over 100. That would be 1.41. If I square that, I'm close, but I'm not close enough to the square root of 2. Okay? And if you see why, if this was the square, if I squared this and was close to 2, this would be 20,000 over 1,000, and I'm not there. What about 1414 over 1,000? Am I closer if I square that? And the answer is yes, but not quite. And the actual thing is if I took, and I'm trying to get more digits, bear with me, and I'm not sure how to do that. There we go. Sorry about that. I'm going to put that on float 12. So that if I do square root of 2 now, we'll have, there we go. There's a lot of digits. Okay. So let me find 1, 4, 1, 4, 2, 1, 3, 5, 6, 2, 3, 7. Now, the real, how many is that? That's 1, 4, 1, 4, 2, 1, 3, 5, 6, 2, 3, 7. Okay, there it is. Right? That is the square root of 2 approximated as a fraction. Now, if I square this big number, I should get something. This should be 2 over 1, right? That's 2. If I square the square root of 2, I get 2, but I'm not even close. I'm still not even close to 2. Well, I'm pretty close to 2, but these last 4 numbers here aren't near 2. Okay, so that means that the square root of 2 is not rational. But let's look at a better proof of why. And I don't want to do a lot of proofs, but this one is an important proof. And this is, without a doubt, proves that the square root of 2 is not rational. Okay. The square root of 2 cannot be expressed as the quotient of 2 integers. Other than this big thing, this means that the square root of 2 is going to have even more numbers, because even more digits than this, and it does. Okay, we can get a whole lot of them. Okay, they go on forever and ever and ever, and they never repeat. Okay, they never repeat, and they never stop. They go on forever. They're irrational. Okay, so let's say I have 2 numbers, m divided by n. Okay, this is a fraction, and if I square them, they give me 2. Okay, now the idea behind this is that m and n have no common factors. They are reduced. No common factors. M and n have no common factors. And in big math people language, we call those coprime. You can't reduce these. Okay? And we're going to prove by contradiction that there is no fraction m divided by n squared that equals 2. So what do we want to do? First, well, let's write this as m squared divided by n squared is equal to 2. N cannot be 0, of course. Okay. N is non-zero, and this reduces. So the first thing we'd want to do is multiply both sides by n squared. So let's do that. So we have m squared is equal to 2n squared, if I do that. Okay. Now where am I going here? This means if I take a number and square it and get 2n squared, that means that m is an even number. You can't square a number and it not be even. So m has to be even. Look at So in other words, like if I take 8 and square it, it's going to be 64. Okay, so that means if n is even, that means that it is of the form 2k squared, where k is just another integer. Okay. If m is even, which this indicates, because if I take m and square it, I get 2n squared. This result is an even number. That means that this is even. So that means that 2k squared has to equal 2n squared. So let's square this out. That's going to give us 4k squared is equal to 2n squared. Now let's divide both sides by 2. That gives us 2k squared is equal to n squared. Now what does this mean? This means that n has to be even. Well, that's a contradiction, because here we said that neither one of these have a common factor. Well, if they're both even, they have a common factor. Therefore, m divided by n squared cannot be 2 by contradiction. This is a proof by contradiction, because n and m cannot both be even when I say they're not. Okay? And all of these numbers that we've looked at so far are called real numbers, and they can all be plotted on the real line. Let's look at the closure properties of irrational numbers, and that's what's irrational closure property. So all the rational numbers were closed under addition, subtraction, multiplication, and division. Well, irrational aren't closed under any of them. All we need is one example that shows that irrational numbers, if I add two irrational numbers and don't get an irrational number, it's not closed under addition. Let's prove that why. Here's an irrational number. 3 plus the square root of 3 is an irrational number. Okay, even though it's the sum of two different things, this is an irrational number. If I take this number and subtract the square root of 3, what's that going to give me? 3, right? Not closed. Not closed. If I take, even though that looks like two numbers, it's not. This is an irrational number. It's the only way you can represent mathematically 3 plus the square root of 3. Let's look at its decimal form. 3 plus the square root of 3. Okay, there it doesn't look like a number, but here it does. That looks like a number, right? So if I take that number and I subtract the square root of 3, I get 3. Okay? That means not closed under addition. Even though I subtracted them, let's just say that that's plus negative. It's not closed under subtraction either. What about multiplication? Well, we obviously know that it's not closed under multiplication, because I can take the square root of 2 and multiply it by the square root of 2. What would I get? 2. Not closed under. And then division, I could say I take 3 square roots of 2 and divide by the square root of 2. What's that going to give me? 3. So we're not closed under anything under irrational numbers. Okay? But let's talk about, right before I close, what kinds of numbers are irrational numbers? Where do these come up at? Okay? Types of irrational numbers. Where are you going to see these nasty boogers? The first type that you're going to see very commonly are non-perfect roots. Non-perfect roots. What do I mean by non-perfect roots? Well, the square root of 4 is 2. That's a perfect root. That's going to be rational. But non-perfect, the square root of 5, is going to be irrational. Okay? Cube root of 28 is going to be a non-perfect root. The perfect root would be the cube root of 27, 3 times 3 times 3, right? Non-perfect roots. And they could be any nth root. Okay? The 12th root of 10 is going to be irrational. Okay? But the 12th root of 1, what is the 12th root of 1? It's the only 12th root I know off the top of my head. 1. Okay? What about the 12th root of 0? 0. Okay? Where else? Later in math, you're going to see logarithms. And I'm not going to talk about them. But logarithms are another example of irrational numbers. And I'm not going to go into greater detail until we do the lecture on logarithms. But these are irrational. And another popular are constants that we use, very popular in math. And one of the most popular irrational numbers of all time is pi. And it really chaps me when people say that pi is equal to 3.14. That is false. That is false. What is pi equal to? What is pi equal to? Pi is not equal to anything. It's equal to pi. It's approximately 3.14. Okay, let's look at pi on the calculator. Never stops. Pi never stops. It goes on forever. There's a like Weird Al Yankovic says, I know pi to 1,000 digits. There's people that actually memorize that stuff. There's a Guinness Book of World Record contest where the guy memorizes the most number of digits in pi. They say Euler, a famous mathematician whose number is we're about to look at, he had thousands of these digits memorized. He had a photographic memory. One of the most famous mathematicians of our time had a photographic memory, was blind and was almost near blind and still writing papers when he died. So he was doing all this hard calculus math that he discovered in his head. Crazy. What's another constant? So E. E is another one. And E is probably one of the most used numbers in mathematics. A lot of people say pi is, but when we start taking calculus, you're going to see how famous E is, because there's a lot of behavior that deals with E. And E is very big in trigonometry. You think, where does the exponential function come into trigonometry? You'll see that in post-calculus. Okay? Believe it or not, E is used in trigonometry more than pi is. It's crazy. Okay? And we'll talk about why later. I don't want to. This has nothing to do. Just know that E is irrational. What is E approximately to? E is approximately. Oh, that's not what I wanted to do. Oh, there we go. That's the bolded E I wanted. E is approximately 2.71. There's a lot of digits right there. 281.82846. It goes on for a while. Okay? Forever. Not for a while. It goes on forever. Never repeats a digit. Ever. So those are the types of numbers that we looked at. So let's review and look at the real numbers. All these numbers can be graphed, because you can graph E. It's approximately 2.71. Okay? You can graph approximately where it is, but you can tell that 2.7 is smaller than E. Okay. Let's talk about the real numbers. They're denoted by R. Okay. Review what we just covered. Script R. Okay. Split into two big categories: irrational numbers and rational numbers. I'm just going to write rational. I'm not going to write the word number over and over again. The irrational numbers are denoted by I, and the rational numbers are denoted by Q. irrational numbers have no subsets. They are perfect, non-perfect roots, and pi, e, and so on, and logarithms. There's other ones too. There's other irrational numbers than these. The thing is that their digits never terminate, never repeat. Okay? Digits never terminate and never repeat. Rational number. Rational. Quotient of two numbers. M and N belong to Z. Okay? N not 0. Their digits terminate or repeat. Or instead of just saying terminate, they repeat, because they can repeat zeros. Okay? If I say 1 divided by 2, I'm going to show an example of that. 2 divided by 1.0. Okay, here's an example of 1/2. This is 1/2 repeating. 2 goes into 10 5 times. 5 times 2 is 10. Here's a 0. 2 goes into 0 0 times. 0 times 2 is 0, 0. It repeats zeros. Okay? We don't usually write it like that. We say it terminates. But technically, it really repeats numbers over and over and over. Under the rational numbers, we get the integers. All integers are rational numbers. All integers are rational numbers. If I say negative 300, I can write that as a ratio like this of two integers, negative 300 over 1. Okay? All integers are rational numbers, and those are Z. Under the integers, we get the whole numbers. W. All whole numbers are integers. All integers are rational. Under the whole numbers, we get the natural numbers. N. And I said I wasn't going to write numbers, and there I did it anyway. So that's a review of the real number system and the subsets of real numbers. If you have any questions about this lecture, post a comment, and if I have time, I'll definitely try to answer your question. Or if you need any free tutoring, if you need tutoring, it's not free, I'm sorry, but I will have a sponsored rate. I'll discount 10% if you can tell me the code Euler Math. Okay, if you can post this in any kind of comment, I'll give you 10% off. And my normal rate is $15 per hour. But of course, this lecture is free, and any questions that I have time to answer will also be free. Appreciate your time watching this video. The next video coming up will be properties of real numbers, so we're going to go further into the real numbers about their properties, and that video will be coming out in the near future. Thank you for your time, and I hope everyone has a great weekend.